Welcome to a journey of endless curiosity. In 108 Questions of Why, the phenomenon of auroras, those breathtaking displays of light that dance across the polar skies, has captivated human imagination for centuries. Known as the Northern Lights in the Arctic and the Southern Lights in the Antarctic, these ethereal curtains of color are not merely beautiful, they are a vivid manifestation of the complex interactions between the Earth's atmosphere and the solar wind. To understand why auroras appear near the Earth's poles, one must delve into the intricacies of our planet's magnetic field, the behavior of charged particles from the sun, and the atmospheric conditions that allow these spectacular light shows to unfold. At the heart of the aurora phenomenon lies the sun, a massive ball of nuclear fusion that emits a constant stream of charged particles known as the solar wind. This wind is composed primarily of electrons and protons that are propelled into space at speeds of up to 1 million miles per hour. While the sun's energy is vital for life on Earth, it also poses challenges due to the potential harm these charged particles can inflict on our planet's atmosphere and technological systems. Fortunately, Earth is protected by its magnetic field, a shield generated by the movement of molten iron within its outer core. This magnetic field extends far into space and forms a protective bubble around the planet, deflecting most of the solar wind. However, the magnetic field is not uniform. It has distinct poles where the lines of magnetic force converge. These poles, located near the geographical North and South poles, create regions where the magnetic field is weaker. When the solar wind reaches Earth, the charged particles can penetrate the magnetic field more easily in these polar regions. As a result, the auroras are most commonly observed near the poles, where the magnetic field lines funnel the charged particles toward the atmosphere. Once these charged particles enter the Earth's upper atmosphere, they collide with gas molecules, predominantly oxygen and nitrogen. These collisions occur at altitudes of about 80 to 300 kilometers above the Earth's surface. The energy released during these collisions is what produces the stunning light displays characteristic of auroras. Oxygen, for instance, can emit light in red and green hues, while nitrogen can produce blue and purple shades. The variations in color depend on the type of gas involved in the collision and the altitude at which the interaction occurs. The intensity and frequency of auroras are influenced by solar activity, which follows an approximately 11-year cycle. During periods of heightened solar activity, known as solar maximum, the sun releases more solar flares and coronal mass ejections, sending a greater number of charged particles toward Earth. This increase in solar wind can lead to more frequent and more intense auroral displays. Conversely, during solar minimum, the occurrence of auroras tends to diminish. This cyclical nature of solar activity means that some years are particularly favorable for aurora viewing, while others may yield few sightings. The geographical positioning of the auroras is also a crucial factor. The auroral oval, the region where auroras are most likely to occur, is typically centered around the magnetic poles. This oval can shift and expand depending on the solar wind conditions. When a coronal mass ejection occurs, for example, it can compress the magnetic field, causing the auroral oval to expand equatorially. This means that during particularly strong solar storms, auroras can be seen at lower latitudes than usual, sometimes surprising observers in regions that are not typically associated with auroral displays. The interplay of the Earth's magnetic field and solar wind is not only responsible for the visual spectacle of auroras, but also has significant implications for our planet's technological infrastructure. The charged particles can disrupt satellite communications, navigation systems, and even power grids. The 1989 blackout in Quebec, caused by a geomagnetic storm, serves as a stark reminder of the potential impact of solar activity on modern society. As we continue to explore the depths of space and our relationship with the sun, understanding auroras becomes increasingly important, not only for appreciating their beauty, but also for safeguarding our technological advancements. In addition to their scientific significance, auroras hold cultural and historical importance for various indigenous peoples of the Arctic. Many cultures have woven these celestial phenomena into their mythologies and traditions. For instance, The Sami people of northern Scandinavia have long regarded the northern lights as the spirits of their ancestors, while other cultures have seen them as omens or messages from the divine. These interpretations reflect a deep connection between human beings and the natural world, a reminder of how our ancestors sought to make sense of the mysteries that surrounded them. The experience of witnessing an aurora is often described as transformative. People travel from all over the world to the polar regions, braving the cold and darkness for a chance to witness the lights. The anticipation builds as night falls, and the sky begins to shimmer with faint colors. Then, as if a curtain has been drawn back, the auroras burst forth in brilliant waves of green, pink, and violet, swirling and shifting like a living entity. This spectacle evokes a sense of wonder and humility, a reminder of the vastness of the universe and our place within it. The scientific study of auroras continues to evolve as technology advances. Satellites and ground-based observatories provide valuable data about solar activity and its effects on Earth's atmosphere. Researchers use this information to improve our understanding of space weather and its potential impacts on our planet. The study of auroras also opens doors to broader inquiries about the universe, including the behavior of other celestial bodies and the nature of magnetic fields across the cosmos. In conclusion, the auroras are a stunning natural phenomenon that arises from the intricate dance between the Earth's magnetic field and the solar wind. Their appearance near the poles is a result of the unique characteristics of our planet's magnetic field, which allows charged particles from the sun to enter the atmosphere more readily in these regions. The resulting light displays are not only beautiful, but also serve as a reminder of the interconnectedness of solar activity, Earth's protective mechanisms, and the delicate balance of our atmosphere. As we continue to explore and understand these magnificent displays, we are reminded of the wonder of nature and the ongoing quest for knowledge that drives humanity forward. The auroras, in all their splendor, remain a testament to the intricate and dynamic relationship between our planet and the cosmos, a relationship that continues to inspire awe and curiosity in all who gaze upon their luminous beauty.